They told us the universe is full of stars, but what if most of it is empty? An invisible ocean of nothing stretching 2 billion light years wide, and we are floating right in the middle of it. Here, galaxies fade, gravity weakens, and even light begins to lose its strength. Scientists call it the KBC Void, a vast cosmic hollow so large it might explain why the universe appears to expand faster than it should. Could it be that everything we've measured is wrong because of where we live? Tonight, we enter the silence between galaxies to uncover the greatest hidden structure in the known universe. Prepare to journey through the cosmic void that surrounds our home and discover how emptiness may hold the key to everything. If you love exploring the mysteries of space and science, support this journey by subscribing and leaving a like. It helps our small corner of curiosity keep glowing in the dark. We begin. In the far distances of the night sky, galaxies float like scattered lanterns on an endless sea. Their light, ancient and delicate, drifts for billions of years before touching our eyes. But between those bright islands lies something far greater than the galaxies themselves. Vast, silent spaces of near-nothingness. And here is the strange truth. Our own home, the Milky Way, may sit inside one of these enormous cosmic hollows. Astronomers call it a void, a region of the universe where there are far fewer galaxies, stars and matter than average. Imagine a city seen from above at night. The glowing downtown is busy with lights and motion. Now move far away, toward the outskirts where the streetlights thin and the houses disappear. The air grows still, the darkness becomes wider. That quiet emptiness is what a cosmic void feels like, only stretched to a scale the human mind can barely hold. Scientists estimate that about 90% of the volume of the universe is made of such emptiness. The remaining 10%, the filaments, clusters and walls, form a grand cosmic web. These filaments connect like glowing veins, carrying galaxies and dark matter along invisible bridges of gravity. From a distance, the universe looks like lace or foam or a frozen lightning storm in 3 dimensions. Inside one of the largest of these hollow regions, the KBC Void, we may be drifting even now. This is not a small pocket of space. It is thought to stretch roughly 2 billion light years across, a gulf so large that light itself would need 20 human lifetimes just to cross it. Within this hollow, the amount of matter is lower by about 20% compared to the cosmic average. It is as if the universe has taken a quiet breath here and left us suspended in that pause. When scientists first hinted that we might live inside a void, it sounded impossible. How could something so enormous remain unnoticed? Yet space hides its secrets not by absence but by calmness. A void is not empty like a vacuum chamber. It still holds galaxies, gas, dust and dark energy. But everything is more spread out, more delicate, like a mist instead of a storm. From within, the universe looks almost normal. The stars rise, galaxies spin, light travels and gravity still works. But on the largest scales, the fabric of reality stretches a little faster. Here, where matter is scarce, the expansion of the universe feels freer, less restrained by gravity's pull. It's a subtle difference, but one that can change how we measure time, distance, and even the fate of the cosmos. To sense the size of this hollow, picture yourself standing at its centre. The nearest cluster of galaxies lies hundreds of millions of light years away, dimmed by distance and thin air. The filaments beyond shimmer like ghostly highways. Between them lies the quiet ocean of dark energy, an invisible pressure pushing galaxies apart faster and faster. And yet in this silence there is structure. Even in a void, gravity never stops whispering. Tiny fluctuations left over from the Big Bang grew into knots and strands of matter. Those strands formed the first stars, the first galaxies, the first clusters. The spaces between them became the voids. Over billions of years, the dense regions grew denser, while the empty ones emptied further. The result? A cosmic sponge of matter and space, with us floating inside one of its largest bubbles. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Len Cowie, studied tens of thousands of galaxies across the skies of the Northern Hemisphere. They noticed something curious. The density of galaxies seemed to drop as they looked farther out. The region around our galaxy appeared unusually thin. Their careful maps revealed the outlines of a giant underdense zone. Later, scientists began calling it the KBC Void after their initials. The finding was bold. Could we really be living inside a cosmic hole? The data suggested yes, but the idea raised more questions than it answered. If true, it could explain one of astronomy's biggest puzzles, the Hubble tension, the disagreement between how fast the universe appears to be expanding nearby versus far away. Perhaps, the astronomers thought, our unusual cosmic neighbourhood might be bending our measurements in subtle ways, but that mystery belongs to another part of our story. For now, imagine standing at the edge of this unseen valley. No walls, no borders, only a faint thinning of galaxies as the eye reaches outward. A few bright spirals drift alone in the dark. The emptiness between them is so wide that light, travelling since before humanity existed, may never reach another shore. The air of deep space carries no sound, yet if we could translate gravity into tone, the void would hum at a lower note than any instrument could play. It is not a sound of loss, but of balance, the universe stretching evenly, patiently, as it has for nearly 14 billion years. And inside this vast stillness, life emerged. Here on Earth, a fragile speck surrounded by galaxies and silence, we build telescopes and ask questions. We look out from inside our hollow and wonder what it means that most of existence is in fact emptiness. Some scientists think the void may not be perfectly centered on us. We could be 200 or 300 million light years off to the side, drifting near one of its slopes, but in cosmic terms we are still well within its depths. Others doubt its very existence, suggesting our data is incomplete or shaped by how we look at the universe. The debate continues, quiet but persistent, like an echo in a cavern too large to map. What no one denies is that voids are real, and they shape everything. They guide galaxies into strings, affect the pull of gravity, and influence how fast the cosmos expands. They are the invisible lungs of the universe, exhaling space itself. So tonight, as you imagine the stars above, remember that their light travels through the same hollow we call home. Between every sparkle lies a chasm so deep it can swallow thousands of galaxies whole. Yet within that emptiness, creation still happens. Stars are born, planets form, and consciousness wonders why there is something rather than nothing. The silent hollow around us is not a prison. It is a cradle, a vast, unseen chamber where the universe pauses, perhaps to think about itself. And in that pause we listen. Every great mystery begins with someone who decides to look a little closer. The story of the cosmic void, the invisible space that surrounds us, began not with a discovery in one night, but with the slow, patient work of people who refuse to stop asking questions about what lies beyond the stars. In 2013, 3 astronomers, Ryan Keenan, Amy Barger and Len Cowie, were studying how galaxies are spread across the universe. They worked from observatories in Hawaii, where the clear skies above Mauna Kea opened a window to millions of distant worlds. With powerful telescopes, they collected the light of more than 35,000 galaxies and measured how far each one was from Earth. Each point of light told a story about where matter was dense and where it was missing. At first, their goal was simple, to check whether the number of galaxies changed with distance, but what they found was strange. As they looked farther away, galaxies became more common, yet closer to home, within a few billion light years, their numbers dropped. The universe around us seemed thinner, emptier, like a quiet valley surrounded by busier peaks. This wasn't just a small dip in numbers. The pattern suggested that our part of the universe contained about 20% less matter than expected. That is a lot. In cosmic terms, it meant our region was lighter, less crowded, and expanding a little faster than its surroundings. Keenan and his team began to suspect that we might live inside a giant cosmic void, now known as the KBC Void, named after their initials. The idea was bold and unsettling. If they were right, it would mean the Milky Way and its neighbouring galaxies are floating in one of the largest underdense regions ever recorded, possibly 2 billion light-years wide. To imagine the size of that, picture a bubble so large that hundreds of thousands of galaxies could fit inside it. Light itself, travelling at 300,000 kilometres per second, would need 20 million centuries to cross it. And here we are, right inside that immense invisible bubble, moving slowly through its thin air. When the findings were published, the astronomy community reacted with curiosity and skepticism. Some scientists found the data convincing. Others thought it was just a coincidence, a result of the limited sky surveys available at the time. After all, mapping the universe is not easy. Galaxies are not neatly arranged. They cluster in webs and filaments, and our instruments can only see a small part of the whole structure. Still, the idea would not go away. As larger surveys arrived, including the Sloan Digital Sky Survey, SDSS, and others, they confirmed that voids, huge roundish regions with fewer galaxies, do exist all over the cosmos. These are not mistakes, they are part of the natural shape of space. Voids form as gravity pulls matter together into long filaments, leaving behind pockets of low density. Over billions of years, those pockets grow, joining into supervoids that span unimaginable distances. Keenan, Barger and Cowie didn't even discover the idea of voids themselves. That came earlier in the 1970s, but they were among the first to show that our own galaxy might be inside one. That idea connected many puzzles in modern cosmology, especially the question of how fast the universe expands. For decades, astronomers had measured 2 very different values for the Hubble constant, which describes the expansion rate of the universe. When they measured it nearby, using stars and supernovae, they got a higher number, around 73 kilometers per second per megaparsec. But when they looked at the early universe, through the cosmic microwave background left after the Big Bang, they got a lower number, about 67. The disagreement between these two methods became known as the Hubble tension. If we truly live inside a void, that could explain part of the difference. Inside a region with less matter, space expands a little faster. So from our point of view, nearby galaxies appear to move away quicker than the average cosmic rate. It's not that our instruments are wrong, it's that our neighbourhood is special. The KBC Void might be changing how we see the universe, making it look like expansion is speeding up when, in reality, we are just watching from a hollow. That idea fascinated scientists because it offered a simple physical reason for one of cosmology's hardest questions. But it also raised new ones. If our view is distorted, what else might we be misreading? Could the void make the universe seem younger or older than it truly is? Could it change how we understand dark energy, the mysterious force pushing galaxies apart? Not everyone agreed with the KBC team's interpretation. Some researchers argued that the void isn't deep or wide enough to fully explain the Hubble tension. Others said our galaxy might not be near the centre at all, but drifting near one side. And some believe that the tension itself is a sign of new physics, something deeper than just a local emptiness. Still, the KBC Void has become part of modern cosmological discussion. It appears in scientific papers, lectures and simulations. New surveys like DESI and Euclid are now gathering more detailed maps to test whether this void truly surrounds us. Every year, more data adds small pieces to the puzzle, either confirming or challenging the idea. What makes this story powerful is not just the science, it's the human effort behind it. Imagine spending years looking at faint dots of light, calculating distances, and searching for patterns in what seems like chaos. Then one day, realizing that those patterns might reveal a hole big enough to contain everything we know. That moment of discovery, that fragile blend of doubt and wonder, is at the heart of every great scientific journey. The three astronomers didn't set out to prove we lived in a cosmic hole. They simply followed where the evidence led. And like explorers who discover an unexpected canyon beneath familiar ground, they stood at the edge of a vast absence and gave it a name. Now, when we gaze at the night sky, we can imagine their discovery shaping our view. Every star we see, every galaxy our telescopes capture, is shining within that same hollow. The light crosses billions of empty light years before it reaches us, carrying the quiet message that the universe is not evenly filled. It breathes, it swells, it hollows, and within one of those hollows, we live and dream. So the next time you look upward, remember the people who mapped the dark. They showed us that even emptiness can have structure, that even silence can be measured, and that sometimes the greatest discoveries come not from what we see, but from what is missing. Everything in the universe is shaped by one quiet, invisible force: gravity. It does not roar or flash like lightning. It simply pulls. Over time, it sculpts galaxies, binds stars together, and guides planets in their endless circles. Yet even this ancient power weakens in the great hollows between the galaxies. Inside a cosmic void, gravity's whisper fades until it is barely there at all. Imagine space as an ocean made not of water, but of invisible threads, threads of gravity pulling on everything that floats within it. Where the threads are thick, galaxies gather, merging into clusters. Where the threads are thin, matter drifts apart, leaving behind emptiness. That is what happens inside a void. Gravity loses its grip and expansion takes over. Everywhere in the universe, two forces are always in a slow, silent struggle. One is gravity, pulling matter together. The other is dark energy, pushing everything apart. For billions of years, gravity held the upper hand, forming stars, planets, and galaxies from clouds of dust. But as the universe grew larger and thinner, dark energy began to win. In the vast spaces where matter is scarce, inside the voids, dark energy becomes the dominant force. This is why the KBC Void around us expands a little faster than denser regions. There isn't enough matter to pull back against the stretching of space. You could imagine it like dough rising in an oven. Where the dough is thin, bubbles form more quickly. Where it is thick, they expand more slowly. Our corner of the universe is one of those thin places, a bubble swelling gently in the heat of cosmic time. For scientists, this balance between gravity and dark energy is the key to understanding the universe's fate. Gravity builds, dark energy dissolves. If gravity had been stronger, the universe might have collapsed long ago into a single dense mass. If dark energy had been stronger, galaxies might never have formed. Somehow they reached a fragile balance, allowing stars to shine, life to rise, and time to flow long enough for us to ask why. The idea that dark energy dominates our cosmic neighborhood feels strange because we cannot see or touch it. Yet its fingerprints are everywhere. Observations show that the space between galaxies is stretching faster and faster. Even light, traveling from the farthest reaches, gets stretched and cooled as it moves through this expanding fabric. The universe is not static, it breathes. Inside a void, that breath is a little deeper. The galaxies float farther apart, their motion almost lazy. Gravity's voice, which once spoke in the birth cries of stars, now hums softly in the background. The cosmic web around the void looks like a fog made of faint light, its strands glowing with distant galaxies. But inside, the air of existence is thin and dark energy rules. Scientists sometimes describe the universe as a Swiss cheese, a vast block of matter dotted with bubbles of emptiness. The filaments of galaxies form the solid parts, the voids are the holes. Each hole is a place where gravity once gathered less matter, so expansion had more freedom. Over time, the holes grew, swallowing smaller ones, until they became enormous supervoids. The KBC Void, if confirmed, may be the biggest of all. This quiet expansion has real effects we can measure. Galaxies near the edges of a void move slightly faster outward than those in dense regions. Their light stretches a bit more as they speed away. When astronomers observe them, the difference appears as a redshift, a shift in the colour of light toward the red side of the spectrum. Redshift is one of the most important clues in cosmology. It tells us how fast space itself is stretching, and how gravity and dark energy share their dance. Inside a void, redshift behaves differently. Because gravity is weaker, light loses less energy climbing out of gravitational wells. It travels through smoother terrain. Some researchers even propose that photons, tiny packets of light, may cool slightly slower in such regions. Over billions of years, those tiny effects add up, giving us a slightly distorted picture of the universe's true pace. Think of it like walking across a valley. In dense regions, you climb hills and cross rough ground. It takes time and effort. Inside a void, the path is smooth and downhill all the way. Light, in a sense, takes that easier route. It glides through emptier space, hardly slowed by gravity's pull. And so, what we see from within the void might look subtly different from what the universe looks like elsewhere. There are still mysteries hidden in this quiet tug-of-war. We do not fully understand what darker energy really is. Is it a property of space itself, a kind of built-in stretch? Or is it something deeper, a new form of energy that fills every corner of reality? No one knows. We only know its effect, a gentle acceleration that grows stronger with distance. Some scientists have suggested that gravity itself might change its behavior on cosmic scales. Perhaps, they say, Einstein's theory of general relativity, the foundation of our understanding of gravity, may not hold true in the deep emptiness of a void. Maybe there are hidden rules that only appear when space becomes extremely thin and calm. So far, observations agree with Einstein, but the questions remain open. Even in this quiet, gravity has work to do. Small galaxies still orbit one another. Streams of dark matter still weave invisible bridges across space, and every bit of matter still feels every other bit, no matter how faint the connection. Gravity never turns off, it only whispers more softly here. Our own galaxy, the Milky Way, feels those whispers as it moves through space. It is carried not just by the general expansion of the universe, but also by local flows of matter, rivers of galaxies drifting toward denser regions and away from emptier ones. These gentle currents are guided by the shape of the void itself, a slow migration across cosmic time. So we float, held between gravity's pull and dark energy's push. We are like dust in a silent wind, carried by forces we cannot see but can measure with astonishing precision. Each observation, each equation, tells us that even emptiness has structure, and that gravity's faint voice still echoes across the endless dark. The universe is not just stars and planets. It is a living balance of pressure and release, of contraction and expansion. The void around us is not lifeless. It is part of that rhythm. It is the space between notes that allows the cosmic symphony to breathe, and as we listen, our instruments pointed toward the dark, we begin to hear that faint whisper again. It tells us that even in silence, the universe is alive, still building, still changing, still expanding into forever. How fast is the universe expanding? It sounds like a simple question, but the answer has divided scientists for years. At the heart of that mystery lies a strange conflict known as the Hubble tension, a disagreement about the speed at which space itself is stretching. And the most curious part of all is that this problem might be connected to the place we call home, the vast cosmic void that surrounds us. To understand this, we must first talk about what the Hubble constant is. In the early 1900s, astronomer Edwin Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they seem to be going. This relationship showed that the universe is not fixed. It is expanding like a balloon being slowly inflated. The rate of that expansion became known as the Hubble constant. But in the decades since, scientists using different methods have not agreed on what that rate actually is. When astronomers measure the early universe, looking at the faint afterglow of the Big Bang called the cosmic microwave background, CMB, they find an expansion rate of about 67 kilometers per second per megaparsec. That means that for every megaparsec, or 3.26 million light-years of distance, space expands by 67 kilometers per second. But when they measure galaxies and stars closer to us, in the local universe, the number comes out higher, around 73 kilometers per second per megaparsec. This difference of just a few kilometers per second may not sound like much, but in cosmology, it's huge. It means that either the early universe and the modern universe follow different physical rules, or that something about our measurements is being distorted. The tension between these two results has grown stronger every year, even as new data pours in. Some researchers believe this Hubble tension could be explained by the KBC Void, the enormous underdense region we might be living inside. The idea is simple. If our part of the universe contains less matter than average, then galaxies near us would appear to move away faster because there is less gravity holding them back. In other words, we might be living in a kind of cosmic bubble that expands more quickly than the rest of the universe. Imagine standing in the middle of a valley surrounded by distant mountains. When you throw a ball, the echo from the mountains takes longer to return than it would if you were standing closer to the walls. To your ears, it might sound as if the valley is larger than it really is. In a similar way, living inside a cosmic void might make us misjudge how far galaxies truly are, and how fast they are moving. If this is true, the higher local measurement of the Hubble constant might not be wrong. It's just local. It would describe the expansion within our underdense region, not the entire universe. The lower value, measured from the early universe, would describe the global rate. Both could be correct, just describing different scales of reality. This idea gives a poetic twist to our place in the cosmos. What we see as the universe might be subtly shaped by where we stand within it. We're not at the centre of all things, but we're inside a region that bends our perception of time and distance, like a lens made of near nothing. Still, not everyone agrees. Some scientists think the KBC Void, while real, is not large or deep enough to cause the Hubble tension. Their models show that even a 20% drop in matter density wouldn't create such a big difference in expansion rate. Others believe the tension points toward new physics, something that goes beyond Einstein's theory of gravity. Perhaps dark energy changes over time, or new particles influence the early universe in ways we don't yet understand. These debates are healthy. Science grows through argument, not agreement. Each new observation pushes the limits of what we know. Powerful telescopes and surveys like DZ, Euclid, and the James Webb Space Telescope are now collecting data with unprecedented precision, measuring galaxies and supernovae across billions of light-years. With every new discovery, the picture becomes clearer and sometimes stranger. For example, when astronomers measure the brightness of certain exploding stars called Type Ia supernovae, they can calculate how far away those galaxies are and how fast they're moving. These stars act like cosmic lighthouses, always shining with roughly the same brightness, so any change tells us about distance. But when those supernovae are observed within our local region, their patterns sometimes differ from those farther away. It's as if light travelling through our cosmic neighbourhood behaves a little differently, perhaps because space itself expands unevenly here. This unevenness is what the KBC Void hypothesis tries to explain. Within our underdense bubble, dark energy might dominate slightly more, pushing galaxies apart at a faster rate. Beyond the void, where matter is denser, gravity's pull slows expansion down. If our telescopes measure only from inside the bubble, we could be fooled into thinking the entire universe expands faster than it really does. One could say that the universe is a stage with a flexible floor, each region dancing to its own tempo. Some steps are fast, some slow, but together they create the music of cosmic expansion. From where we stand, we only hear our part of the song, but there is beauty in this uncertainty. It reminds us that every measurement we make is not just about the cosmos, it's also about perspective. We are creatures looking outward from a single, small corner of space, trying to measure something infinite. Our tools are powerful, yet our position colours everything we see. Some philosophers of science have compared this to standing in a fog. You can see a few meters ahead, perhaps even sense the shape of distant hills, but you cannot see the whole landscape. The universe, too, hides its full form behind that fog of scale and distance. And perhaps, inside our quiet hollow, we're in one of the foggiest parts of all. Yet the mystery is not discouraging. It's inspiring. Every disagreement, every question about the Hubble constant drives humanity to build better telescopes, to think deeper, to reach farther. Whether the answer lies in the KBC Void, in dark energy, or in something we haven't imagined yet, one truth remains. The universe is still unfolding before us, and we're still learning how to measure its breadth. In the silence of deep space, that breath continues, slow, steady, and endless. And as we measure, argue, and dream, we're reminded that to understand the cosmos is also to understand how small and how extraordinary our own place within it truly is. Close your eyes and imagine the universe not as a flat picture of stars, but as a living structure. An enormous three-dimensional web that stretches farther than sight itself. It looks a little like soap bubbles packed together, or a sponge glowing softly in the dark. The bright lines and knots are galaxies and clusters. The darker spaces in between are the voids, huge, roundish regions where matter is thin. This is what scientists call the cosmic web, the large-scale skeleton of everything that exists. Billions of years ago, this structure began as something much smaller, tiny ripples in the newborn universe. After the Big Bang, space was filled with a nearly even mix of matter and radiation. But in some places, the density was just slightly higher, maybe 1 part in 100,000. Those tiny differences were enough for gravity to start its slow, patient work. Wherever matter was a little denser, gravity pulled in more, creating knots. Wherever matter was lighter, gravity pulled it away, leaving hollows. The dense parts became the bright threads of galaxies. The hollows became the voids. You can picture it as bread dough rising in an oven. The yeast pushes outward everywhere, but the air collects into big bubbles. The thicker dough around those bubbles forms the structure that gives the loaf its shape. In the same way, the early universe expanded, but matter clumped together along invisible lines, leaving behind enormous cosmic bubbles. The process took billions of years, guided by the silent pull of dark matter and the steady push of expansion. When astronomers map the sky today using powerful telescopes, they see this foam-like pattern clearly. Surveys such as the Sloan Digital Sky Survey and BOSS have measured the positions of millions of galaxies. When plotted in 3D, they reveal a cosmic honeycomb, thin walls of clustered galaxies surrounding empty rooms that can span hundreds of millions of light-years. These rooms are the bubbles of creation. It might sound strange to call emptiness creative, but without these spaces, galaxies would never have taken the shapes we see today. The voids give structure breathing room. As dense regions pull in matter, the surrounding emptiness pushes outward, helping the web stretch and balance. In that slow dance, galaxies form, collide and merge, creating stars and planets, and eventually the conditions for life. Our own galaxy, the Milky Way, lives along one of those glowing filaments, drifting inside the edge of the vast KBC Void. The galaxies around us are like pearls on a thread, connected by gravity but separated by immense distances of darkness. If you could fly outside the Milky Way and look back from far away, you'd see that our galaxy is part of a long, delicate bridge of light suspended in the middle of almost nothing. Scientists think that about 90% of the volume of the universe is made of these voids. That means most of existence is not solid or bright, but thin and open. Yet this emptiness is not truly empty. It contains traces of hydrogen gas, faint radiation, and enormous flows of dark matter, an invisible substance that makes up most of the universe's mass. Dark matter forms the hidden scaffolding of the cosmic web, guiding where galaxies grow and how they move. Some computer simulations show how this web evolved. They begin with a simple map of early fluctuations, tiny ripples of density, and let the laws of physics run for billions of years. What emerges looks uncannily like the real universe, a glowing web with filaments and voids. The largest voids merge over time, while small ones collapse or get squeezed by expanding walls of matter. The picture is alive, changing slowly as the universe continues to stretch. One famous pattern inside this web is called the baryon acoustic oscillation, or BAO. Long ago, before atoms formed, the universe was filled with hot plasma. Sound waves rippled through that plasma, leaving behind rings of slightly higher density. Today, those ancient ripples are frozen into the distribution of galaxies, roughly 490 million light-years apart. Astronomers use that distance as a standard ruler to measure how fast space expands. The BAO pattern also confirms the cosmic web's bubble-like design. Each ripple defines the spacing between dense filaments and wide voids. If you could drift through these vast spaces, you would travel for billions of years without seeing another galaxy. Yet even there, physics continues its quiet work. Light bends as it passes through the changing density of space. Temperatures shift by a fraction of a degree. Time itself stretches ever so slightly. In the deepest parts of the voids, dark energy's push is strongest, speeding up the separation of the galaxies. Some researchers wonder if these bubbles will one day grow so large that they isolate regions of the universe completely. In that far future, each cluster of galaxies might drift away from all others, surrounded by darkness forever. To any observers living then, the cosmic web will seem to have vanished. Their sky will hold only a handful of local stars, and the rest of creation will lie beyond their reach. In a way, the universe will have folded into islands of light floating in an endless black sea. But for now, we can still see the web's full beauty. Through the lenses of giant telescopes, astronomers trace the patterns of galaxies, mapping the outlines of the voids. Each survey adds more detail, revealing where the universe is thick and where it is thin. Some maps even show our local supercluster, called Laniakea, meaning immense heaven in Hawaiian, a fitting name for the vast region of space that includes the Milky Way and the surrounding filaments. Beyond Laniakea lies the dark gulf of the KBC Void, a cosmic room so wide that its walls are still faintly unknown. There is something humbling in this vision. We often think of creation as adding more matter, more light, more life. Yet the universe also creates by removing, by allowing space to open, by giving room for things to grow. The voids are the pauses between the notes of existence, the silences that make the music possible. When you look up at the night sky, you might see a few hundred stars with the naked eye. But remember, between those stars, between every galaxy, lies the greatest part of reality, the unseen bubbles that hold it all together. The cosmic web is not just a pattern. It is the memory of the universe's own birth, frozen in space and time, and somewhere, inside one of its largest bubbles, a small planet spins beneath a thin sky, wondering how such beauty could rise out of so much nothing. Long before the first stars were born, before galaxies formed or light had colour, the young universe glowed with a soft, even warmth. It was filled with energy and particles dancing together in a bright, foggy soup. When that fog finally cleared, around 380,000 years after the Big Bang, light could travel freely for the first time. That ancient light still fills the universe today. We call it the cosmic microwave background, or CMB, the oldest light we can see. The CMB is like a photograph of the universe when it was just a baby. It is faint, but everywhere. If you could tune your television to an unused channel, a small part of the static you'd see would be from this cosmic glow. For scientists, this faint radiation is a treasure map. It tells us about the universe's early shape, its temperature, and even how matter was arranged long before galaxies appeared. But the CMB also carries echoes of what happened later, when light crossed the huge cosmic structures that formed over billions of years. As that ancient light travels through the universe, it passes through galaxy clusters, filaments, and, most mysteriously, the voids. These massive regions of underdensity change the energy of the photons ever so slightly. The result is a pattern of tiny hot and cold spots in the microwave sky. Each one is a whisper of the landscape that light has crossed. One particular effect of this journey is called the integrated Sachs-Wolf effect, often shortened to ISW. It happens because light feels gravity, even though it has no mass. When a photon enters a gravitational well, like the dense region around a galaxy cluster, it gains a little energy. When it climbs back out, it loses that same energy. Normally this exchange cancels out, but the universe's expansion changes things. If space stretches while the photon travels, the gravitational well becomes shallower. The photon cannot lose all the energy it gained on entry, so it escapes a little warmer. Now, imagine the opposite case, a void, where gravity's pull is weaker and space expands faster. When a photon crosses a void, the underdensity deepens as the universe expands. The photon falls into the shallow gravitational hill, loses energy, and climbs out into an even emptier space, leaving slightly colder than before. This gentle cooling is what creates faint cold patches in the CMB. These signals are incredibly weak, but astronomers have learned to find them. They combine CMB maps from satellites like WMAP and Planck with galaxy surveys that show where matter and voids lie. When they overlap the two maps, faint patterns emerge. Cold spots where the CMB light passed through large voids, warm spots where it crossed dense clusters. One of the most famous of these is the CMB cold spot, a region in the southern sky slightly cooler than its surroundings. Some scientists think it may be linked to a massive supervoid, perhaps the Eridanus supervoid, lying between us and that part of the sky. Others believe the cold spot is just a random fluctuation left over from the early universe. The debate continues, but it shows how sensitive the CMB is to the hidden structure of space. If the KBC Void around us is real, and as large as some measurements suggest, it too would leave a fingerprint on the CMB. The effect would be subtle, a faint shift in temperature and pattern across a wide area of the sky. Detecting it requires careful comparison between cosmic maps, filtering out the noise of billions of years of expansion and light. Some studies claim to see hints of it, others find no clear evidence yet. The beauty of this science is that it connects the smallest thing we can measure, tiny changes in light, to the largest thing imaginable, the shape of the entire universe. The CMB is our messenger across time. It has travelled for nearly 13.8 billion years, carrying the story of everything that has ever existed. Every photon in that microwave background has passed through countless voids and clusters, collecting memories of the cosmos as it went. To imagine what this means, think of the universe as a great sea and the CMB as waves crossing it. As they travel, the waves rise and fall over deep trenches and high ridges, the voids and filaments of matter. By studying the pattern of those waves when they finally reach us, scientists can map the unseen landscape beneath. It's like listening to an echo and knowing the shape of the room it came from. The data from the Planck satellite released in the 2010s showed the CMB in incredible detail, tiny temperature differences of just 1 part in 100,000. From these differences, we learned how matter first clumped together, how fast the universe expanded, and even how much of it is made of dark matter and dark energy. The map also confirmed the flatness of the universe on large scales, supporting Einstein's theory of general relativity. But it also hinted that our cosmic neighbourhood might not be completely uniform. Some regions appear slightly more stretched or cool than the average, giving room for ideas like the KBC Void. Of course, none of this can be seen with the naked eye. To us the sky looks calm and bright. But in those microwaves, far beyond the range of human vision, the entire story of cosmic history is written in faint ripples of temperature. Each ripple is a footprint of gravity, expansion, and time itself. Even now, new missions are being planned to observe the CMB with more precision. The Simons Observatory in Lightbird will soon scan the sky to detect polarization, the twisting of light caused by early cosmic waves and later interactions with structures like voids. These observations may finally tell us how much the emptiness around us has shaped the universe we see. There is something deeply poetic in this idea. Light from the dawn of time passes through endless space, whispering as it goes, carrying the memory of what it has touched. When it reaches us, billions of years later, we read those whispers like ancient letters written on the sky. They tell us about the great cosmic hollows, the galaxies that never met, the empty places that shaped everything. And somewhere in that endless pattern, hidden in the noise of eternity, may lie the faintest echo of our own home, the mark of the void we live in, softly imprinted on the oldest light in existence. When we look into the night sky, we believe we see the universe as it truly is. Stars shine, galaxies glow, and the dark between them feels calm and endless. But what if much of what we see is only part of the story? What if the universe, in its quiet and patient way, lies to us, not out of cruelty, but because of where we happen to stand inside it? This strange thought begins with a simple truth. Everything we know about the universe comes from light. We cannot step outside space to look at it from afar. We must observe from within, measuring how light moves, bends, and fades. And if we're inside a void, a great hollow where matter is thin and space expands faster, then that light might be telling us a slightly distorted version of reality. Imagine living inside a bubble of glass. The air inside is warm and light, the walls gently curved. When you look out, objects beyond the bubble seem slightly shifted, stretched by the curved surface. The farther you look, the more the outside world bends and changes. Living inside a cosmic void may do something similar. It bends the way we see time, distance, and expansion, making the universe appear different than it might look from elsewhere. For decades, astronomers have worked under a guiding idea called the cosmological principle. It says that on large scales the universe looks the same everywhere. No special places, no special directions. This principle helps make the equations of cosmology simple and elegant. But if the KBC Void truly surrounds us, then we might be sitting in an unusual patch of space where that rule doesn't fully apply. The universe may not be perfectly even after all. Inside a void, gravity's pull is weaker, and expansion runs slightly ahead. That means light from distant galaxies may travel through space that is stretching faster than average. As it does, its wavelength grows longer, shifting toward the red end of the spectrum. This is what scientists call redshift, a key tool for measuring how far away and how fast something is moving. But if the local expansion is different, our redshift readings can mislead us. We might think galaxies are moving faster or are farther away than they truly are. This could explain some of the mysterious differences between what we measure nearby and what we see in the far universe. For instance, local galaxies seem to recede faster, leading to a higher Hubble constant. But maybe the fault is not in the galaxies, it's in our environment. We live in a faster expanding pocket of space. From our position, everything appears to be rushing away slightly quicker than it would from an average spot in the cosmos. It's a bit like sitting in a small boat drifting down a wide river. The current around your boat is smooth and gentle, so when you look at the shore, it seems to slide past at a certain speed. But downstream, the river narrows and speeds up, while upstream it widens and slows. If you assume the entire river flows at the same rate, your measurements will be wrong. You're just seeing the world from one moving patch of water. In the same way, we see the universe from our moving patch of space, the KBC Void, and that motion might trick us into thinking the cosmos behaves differently than it does elsewhere. Some scientists have even suggested that this could make the universe appear younger than it really is. If our local space expands faster, then when we look outward, the rest of the universe seems to have aged more slowly. Time itself, stretched by emptiness, might tick differently here. That idea feels strange, but not impossible. Time and space are linked, and both are shaped by the distribution of matter. Einstein's theory of general relativity tells us that mass bends space-time like a heavy ball bending a soft sheet. Where there is less mass, like in a void, the sheet is flatter and smoother. Light moves differently there, and so does time. Inside our cosmic hollow, clocks could run a tiny bit faster compared to clocks in denser regions. The effect is small but real. The result is a kind of cosmic illusion. When we measure distances, brightness, and motion, we are also measuring the shape of the bubble we live in. The data we collect carries the fingerprint of our position in the universe. That's why cosmologists spend so much effort correcting for local effects. They want to peel away our bubble's influence to see the pure global universe beneath. Still, it's humbling to think that reality itself may depend on where we stand. We often imagine the universe as a clear window. Look through, and you see truth. But it is more like a mirror made of moving glass. What we see reflects both the universe and our place inside it. And yet, there is comfort in this thought too. It reminds us that the universe is alive with complexity. Even emptiness is not simple. The void around us shapes how we understand everything, but it also makes our existence possible. If the universe were perfectly uniform, with no hollows or clusters, no valleys or peaks of gravity, then no galaxies would have formed, no stars would have burned, and no life would have risen to ask these questions. Sometimes, people hear about the KBC Void and feel uneasy. They imagine we live in a cosmic desert, a lonely bubble cut off from the rest of creation. But in truth, this emptiness connects us more deeply to the whole. The same forces that shape the void also shape the filaments and clusters. Every atom, every beam of light, moves to the same ancient rhythm of expansion and gravity. We are part of that music no matter where we stand. In science, illusions are not failures, they are clues. When the universe lies to us, it is inviting us to look closer, to measure again, to refine our understanding. Each distortion teaches us more about the grand design we inhabit, and so we keep watching, mapping, comparing, listening. We study the flow of galaxies, the shimmer of ancient light, and the subtle tug of gravity. Bit by bit, we correct the universe's gentle tricks and glimpse the truth behind them. In the end, perhaps the universe does not lie at all. It simply speaks a language we are still learning to understand. A language written in light and emptiness, in time and distance. A language that tells us, in its own quiet way, that where we are shapes what we see. All around us, galaxies move, not in silence, but in slow, graceful rivers across the great cosmic web. From our point of view, it may seem as if everything drifts smoothly away as the universe expands. Yet, beneath that simple flow, there are hidden currents. These invisible streams of motion, shaped by gravity and emptiness, are what astronomers call peculiar velocities, movements that happen not just because of expansion, but because of the push and pull of matter and the hollow spaces between it. Even our own galaxy, the Milky Way, is not still. It rushes through space at nearly 600 kilometers per second. That's about 1.3 million miles per hour, relative to the background of the universe. To us, it feels like rest. But to the universe, we are moving through the fabric of space, carried by gravity's faint currents, sliding through the unseen waters of the void. Imagine standing beside a calm sea. On the surface, the tide slowly rises and falls, but beneath, there are deeper streams flowing in different directions. Galaxies move in much the same way. The overall expansion of the universe is like the rising tide. It pulls everything apart. But underneath that, there are complex smaller motions caused by the gravitational pull of nearby clusters and the gentle push of nearby voids. In regions where matter is dense, gravity pulls galaxies inward, creating flows toward clusters. In underdense regions, like the KBC Void, galaxies drift outward, away from the emptiness. This slow outward flow gives the void its shape, like water spreading across the edge of a basin. It's this motion that helps astronomers trace where the hidden voids are, even when they can't see them directly. When scientists map the positions and velocities of thousands of galaxies, they find that their paths often line up, forming great bulk flows, streams of galaxies moving together through space. One of the most famous examples is our own local motion toward a region called the Great Attractor, a gravitational center about 150 million light-years away. Our Milky Way, along with hundreds of thousands of other galaxies, is being slowly drawn toward it, like leaves drifting toward a distant whirlpool. At the same time, we're moving away from the emptier spaces, the voids that lie behind us. In particular, the KBC Void may be gently pushing us outward, adding to our peculiar velocity. It is as if we are caught between two great forces, attraction to the dense superclusters ahead and repulsion from the deep hollows behind. This delicate balance of pull and push shapes the motion of everything around us. Astronomers measure these movements using both light and gravity. When galaxies move toward us, their light shifts slightly toward blue. When they move away, it shifts toward red. By studying these red shifts and blue shifts, scientists can map the hidden flow lines of the cosmic web. It's a bit like dropping floating markers into an invisible river to watch which way the water runs. The patterns they find are stunning. Some galaxies drift along narrow filaments that stretch for hundreds of millions of light years. Others swirl near clusters, orbiting slowly before being pulled in. And around the vast empty regions, the flow of galaxies curves gently outward, like air expanding from a balloon. These are the rivers of motion that shape the living geometry of the universe. One of the most fascinating things about these motions is that they give us clues about dark matter, the invisible substance that makes up most of the universe's mass. We can't see dark matter directly, but we can see how its gravity pulls on galaxies. The speed and direction of those galaxies tell us where the hidden mass lies. It's like watching the wind blow across tall grass. You can't see the wind itself, but you can trace its path by how the blades move. The KBC Void too influences these flows. Because it contains less matter, it has less gravitational pull. So galaxies at its edge feel a gentle push away from it, sliding toward the denser walls beyond. Over billions of years, this motion slowly changes the shape of the void, stretching it larger and smoother. Our galaxy's motion, our peculiar velocity, may partly be a response to that slow expansion, a drift outward from the heart of emptiness toward brighter cosmic shores. When scientists calculate the direction of our movement using the cosmic microwave background, they find a small but clear tilt in the radiation. One side of the sky appears slightly warmer, the other slightly cooler. This temperature difference happens because of our motion through space. As we move toward one direction, the ancient light of the universe looks a bit compressed, bluer, and as we move away from the opposite direction, it looks stretched, redder. It's a cosmic Doppler effect, proof that even the largest structures in the universe are in motion. The most poetic part of all this is that motion never truly stops. Every galaxy, every cluster, every particle of dust is on a journey that began with the Big Bang and continues endlessly. The universe has no still point, only flows within flows, movement layered upon movement. Even the void, which seems like the definition of stillness, is alive with expansion, its boundaries breathing out into the greater cosmos. Some scientists think that as the universe keeps expanding and dark energy becomes stronger, these rivers of motion will slow and fade. Galaxies will drift so far apart that gravity can no longer pull them together. Each cluster will become an isolated island, surrounded by growing darkness. But that time lies trillions of years ahead. For now, the rivers still flow, and we are part of their gentle current. It's easy to feel small in all this. A galaxy is already vast beyond imagination, yet it moves through an even vaster sea. And within that galaxy, our tiny planet circles a small star, unaware of the great journey it's part of. But smallness does not mean insignificance. Every current, no matter how faint, helps shape the flow of the universe. The motion of our galaxy, the drift of our stars, even the beam of light that leaves Earth tonight, all add to the story written across space. We may never feel this motion, but it defines everything. The rivers of galaxies, the pull of gravity, the slow escape from the void. Together they remind us that the universe is not static or frozen. It is alive, in constant movement, shaped by both fullness and emptiness. And as we glide along these cosmic streams, we are carried not toward an end, but toward a deeper understanding of how beautifully connected it all is. Light is the universe's oldest traveller. Long before life began, long before Earth even existed, light was already on its endless journey, moving through space at 300,000 kilometers per second, never stopping, never resting. Every beam that reaches us tonight carries a story from somewhere far away. The glow of newborn stars, the flare of dying suns, the whisper of galaxies beyond imagination. Yet light is not just a messenger. It is also a witness. As it moves, it feels the structure of the universe around it. And nowhere does that story change more quietly, more beautifully, than when light crosses emptiness. When light travels through a cosmic void, it moves through regions where there is very little matter, almost no dust, gas, or galaxies to block or bend its path. Space there is smoother, thinner, and less curved by gravity. You might think that means light travels without any change at all, but in truth, even emptiness shapes it. The expansion of the universe stretches the very space that light moves through. As that space stretches, the wavelength of light stretches too, turning bluer light into redder, colder light. This is what scientists call redshift, the colour signature of an expanding cosmos. In denser regions, gravity bends light more strongly. It can curve its path, slow it down, or even make it take longer to reach us. This bending is called gravitational lensing, and it lets astronomers see invisible things, like the hidden presence of dark matter. But inside a void, where gravity is weak, light behaves differently. It flows in nearly straight lines, hardly bending at all. The lack of matter means fewer detours and less distortion. Yet, because the space itself is expanding faster inside the void, light leaving a distant galaxy loses more energy. It gets stretched further. You can think of it this way. Light is like a sound travelling through air. When air is dense, sound moves one way. When air is thin, it moves differently. Inside the cosmic hollow, the air of space is thinner, and so the song of light changes pitch as it crosses the emptiness. By the time it reaches us, the tune carries the signature of the void, the mark of how the universe has stretched and grown since that light was born. Scientists use this stretched light to learn about the size and shape of the voids. They measure how much redshift changes from one side of a void to the other. When light crosses a large underdense region, it should cool slightly, leaving a faint imprint in the background of cosmic radiation. This effect is subtle, but it can be seen when many measurements are combined. It's another way the universe quietly reveals its secrets, not through loud signals, but through the tiniest shifts in colour and energy. The KBC Void, if it truly surrounds us, has been shaping light for billions of years. Every photon that enters this hollow, whether from distant galaxies, exploding stars, or the early universe, changes just a little as it crosses. The difference is so small that it can only be detected by comparing enormous sets of data, but once found, it tells us how the universe breathes. Light in this way is like dust on a river's surface. It floats along, revealing how the current flows beneath. Sometimes the light's journey is not smooth. When photons pass near the edges of a void, where the density begins to rise again, they may experience a gentle gravitational tug. They fall slightly toward the dense wall, then climb out again, losing a hint of energy in the process. To an observer, this can look like a faint cold spot in the cosmic background, a memory of the light's encounter with emptiness. This interaction between light and gravity is also one of the most direct proofs of Einstein's theory of general relativity. He predicted that gravity doesn't just pull on mass, it curves the very fabric of space and time, guiding how light moves. Decades later, astronomers confirmed this prediction by observing how starlight bends around the sun during an eclipse. On much larger scales, we see it again as light bends around galaxies and clusters, forming Einstein rings, circles of distorted light billions of light years away. But the cosmic void adds another chapter to this story. Here, gravity doesn't bend light strongly, it releases it. Light passing through emptiness seems to sigh in relief, escaping the pull of matter and stretching freely into longer wavelengths. What's even more fascinating is that light does not just tell us about the past, it creates the past we see. Because light takes time to travel, looking farther into space means looking back in time. The light from the nearest star, Proxima Centauri, takes over 4 years to reach us. The light from the Andromeda Galaxy takes more than 2 million years, and the faintest galaxies seen by our telescopes send us light that began its journey over 13 billion years ago, when the universe was young. So when we gaze into deep space, we are really seeing layers of time stacked one upon another. The farther we look, the younger the universe becomes, until we reach the soft glow of the cosmic microwave background, the afterglow of the Big Bang. But that ancient light too has crossed many voids to reach us. Its temperature, direction, and energy all carry the fingerprints of those empty spaces. Each photon is like a postcard stamped by every region it travelled through, each void leaving its unique mark. To understand how light crosses emptiness is to understand how the universe tells its story. Every faint signal that reaches our telescopes, every pulse of radio waves, every glimmer of starlight, is a letter written in the oldest language there is. Scientists decode that language by turning colours into numbers, brightness into distance, and distortion into shape. From that code, we learn how vast the cosmic voids are, how fast the universe expands, and how gravity, and dark energy weave the fabric of reality. There is also poetry in it. Light is the universe remembering itself. When a photon leaves a distant star, it begins a journey that may last longer than any world, longer than life itself. It may cross countless galaxies and traverse unimaginable stretches of darkness. And when, by chance, it finds our tiny planet and touches the mirror of a telescope, the story it carries becomes known. Every beam of light that reaches us tonight is a survivor of that journey through emptiness. Some began their flight before Earth had oceans, before the Milky Way even formed. They crossed the dark valleys between the filaments, gliding through the quiet spaces where gravity whispers and time slows. And after billions of years, they found us, tiny beings inside a vast cosmic hollow, still trying to understand why the universe shines. Science is built on questions. Every time we think we understand the universe, new evidence appears that forces us to look again. The idea that we live inside a giant cosmic void, like the KBC Void, is one of those questions that divide scientists even today. Some believe it could explain deep puzzles about how the universe expands. Others think it's an illusion created by our limited view of the cosmos. This disagreement is not a weakness. It's how science breathes, always testing itself against the unknown. When Ryan Keenan, Amy Barger, and Len Cowie first published their findings in 2013, the idea was both exciting and controversial. A void 2 billion light-years across sounded almost too large to be real. Many astronomers wondered, could such a structure really exist? Or had the team simply seen a pattern that wasn't there, caused by incomplete data? To test it, researchers turned to massive galaxy surveys, projects that measure the position of millions of galaxies across the sky. The Sloan Digital Sky Survey, SDSS, BOSS, and later the Dark Energy Survey, DES, created enormous 3D maps of the universe. When viewed in these maps, the cosmic web became clear. Filaments of galaxies connected by knots of clusters, with great empty spaces in between. The voids were real, but how large and deep they could get was still uncertain. Some models predicted that supervoids could grow to several 100 million light-years across, maybe even more. But 2 billion light-years? That was pushing the limits of what simulations allowed. Still, the KBC team's data seemed to fit. The density near our region was about 20% lower than average, and the Milky Way sat not far from the centre. This discovery soon connected with another puzzle, the Hubble tension, the mismatch between the local and global expansion rates of the universe. If our region really were underdense, it could expand slightly faster, making the local Hubble constant appear higher. Some cosmologists embraced the idea, others were cautious. Critics argued that the void, though real, wasn't big enough or deep enough to explain the full difference. Even the largest hole can't fix the tension, some said. They believed the disagreement between the two expansion measurements must come from something else, perhaps new physics, a changing form of dark energy, or errors in our instruments. The debate soon spread to every corner of cosmology. Scientists proposed dozens of explanations. Maybe our understanding of gravity breaks down on very large scales. Maybe light behaves differently in extreme conditions. Maybe there are unknown particles influencing cosmic expansion. Or perhaps, some said, the void idea was correct but incomplete. It could be one piece of a much bigger picture. To test these possibilities, teams began searching for similar supervoids elsewhere in the universe. And indeed, they found them. Vast, empty regions like the Eridanus, Supervoid, the Bootes Void, and others. Each one was different in size and shape, but all showed that the universe contains more structure than once thought. The cosmic web is not perfectly uniform. It's a living pattern of light and darkness. Still, the KBC Void remains special because it's where we live. That makes it difficult to study. From inside, we can only measure the galaxies around us, not the full 3D shape. It's like trying to understand the size of a balloon while sitting inside it. You can feel the curve, but you can't see the whole surface. This limitation fuels much of the debate. Some scientists suggest that our surveys may unintentionally exaggerate the emptiness near us. Others counter that the data from independent methods, supernova brightness, galaxy counts, and gravitational lensing, all point in the same direction. Our cosmic neighbourhood is indeed lighter than average. Another complication comes from how we measure distance in space. Astronomers often use standard candles, objects with known brightness, such as type Ia supernovae. But if light travelling through the void behaves slightly differently, then even these standard candles may not be perfectly reliable. Tiny distortions in redshift or expansion could ripple through our calculations, making the void appear smaller or larger than it truly is. To resolve the argument, new missions have begun collecting even better data. The DESI, Dark Energy Spectroscopic Instrument, for example, is mapping over 40 million galaxies to create the most detailed 3D map of the universe ever made. The Euclid Space Telescope, launched by the European Space Agency, is now measuring how dark matter and dark energy shape the cosmic web. The Vera Rubin Observatory, soon to begin its survey, will photograph the entire southern sky every few nights, watching how galaxies and supernovae move and fade. Together, these projects may finally tell us whether the KBC Void truly exists and how much it influences our cosmic perspective. But beyond the technical arguments lies a deeper philosophical question. What if the universe isn't perfectly uniform? What if the cosmological principle, the idea that the universe looks the same everywhere, is only approximately true? If that's the case, then our understanding of cosmology might need to evolve. We might have to accept that the universe is more personal than we thought, that where you are changes what you see. This wouldn't make the universe chaotic, it would make it dynamic, like a grand symphony where every region plays a slightly different tune. In dense clusters, gravity dominates the rhythm. In voids, dark energy takes the lead. Together they form the cosmic music we observe, one that may sound a bit different depending on where we listen. Even as scientists debate, one thing remains certain. The search itself brings us closer to truth. Disagreement is the lifeblood of discovery. Every argument leads to new ideas, new methods, and sharper eyes turned toward the sky. The KBC Void, whether real or only partly real, has already deepened our curiosity. It has forced us to refine our measurements, to think about perspective, and to remember that our cosmic view is not the whole view. In the end, the universe keeps some of its secrets, but it rewards those who ask. And perhaps that is the lesson hidden within the void. Emptiness is not nothing. It is a space for questions, a place where understanding can grow. So the debate continues. Some see a whole, others see harmony. Some see an illusion, others a revelation. But all look upward, to the same vast sky, wondering what truths might still be hidden in the quiet spaces between the stars. The night sky looks peaceful, but behind every shining point of light, there is a window into the infinite. Each telescope we build, each mission we launch, opens that window a little wider. Through these instruments, humanity peers not only into space but into time itself, searching for the hidden structure of the universe, and perhaps for proof that we truly live inside a great cosmic hollow. In recent years, new technology has changed how we explore the cosmos. The universe that once seemed still and simple now appears alive, filled with patterns of light and emptiness stretching billions of light years across. These new eyes on the sky, machines of glass, mirrors, and code, are helping us test one of the strangest possibilities of all, that our galaxy floats inside a vast supervoid, the KBC Void, surrounded by distant walls of galaxies like a bubble inside cosmic foam. To understand this structure, scientists are building the most detailed maps of the universe ever made. One of the leading projects is the DESI survey, short for Dark Energy Spectroscopic Instrument, based in Arizona, USA. DESI uses 5,000 small robotic eyes to capture light from galaxies across the sky, measuring how far each one is and how fast it's moving. Over the next few years, DESI will record data from more than 40 million galaxies, creating a 3D map of the cosmic web so detailed that it could show even the faint outlines of voids like ours. Another mission, the Euclid Space Telescope, launched by the European Space Agency, is now orbiting far from Earth. Its job is to look deep into the universe and study dark matter and dark energy, the mysterious forces that shape everything. Euclid observes how light from distant galaxies bends as it travels through space, revealing where invisible matter lies. By studying how light changes across different parts of the sky, scientists hope to see whether some regions, like the space around us, are truly emptier than others. On Earth, Another giant eye is preparing to wake, the Vera C. Rubin Observatory in Chile. This observatory will photograph the entire southern sky every few nights for 10 years. It will capture not just still pictures, but movies of the universe in motion, showing how stars brighten, galaxies drift, and supernovae explode. With this constant watch, Rubin's data will help identify how galaxies are arranged and whether the local universe expands differently from the rest. Each of these missions is like a piece of a vast puzzle. Alone, they show small corners of the picture. Together, they may reveal the full shape of the cosmic web, the filaments, clusters, and voids that give the universe its texture. If the KBC Void exists as described, these new observations will find its edges. If it doesn't, they'll explain why our measurements made it appear that way. For astronomers, this search is not just about numbers, it's about perspective. We want to know where we stand in the grand design. Are we in a dense hub of galaxies or in a quiet corner of cosmic space? Does our location affect how we see the past and predict the future? These are not simple questions, but they touch something deep within us, the desire to know if our view of the universe is unique or universal. Looking into deep space is like reading a book written in light. Every photon that enters a telescope carries information: how long it has travelled, what kind of matter it passed, how space itself has stretched along the way. With powerful computers, astronomers turn these clues into maps and models, recreating the story of the universe from its first breath to today. The more we read, the more we realise how much remains unwritten. New missions will soon join the quest. The Nancy Grace Roman Space Telescope, expected to launch later this decade, will scan wide portions of the sky with unmatched clarity. It will search for supernovae, measure how galaxies cluster, and refine the rate of cosmic expansion. Together with Euclid and Rubin, Roman will give us a layered view of the universe, near and far, dense and empty, past and present. And beyond them all, the James Webb Space Telescope continues to peer deeper into the past than any instrument before it. Webb's golden mirrors can detect the faintest galaxies, those born less than 1 billion years after the Big Bang. Many of those galaxies lie near the edges of massive voids, tracing the same structures that define our universe today. The light Webb catches has crossed not just billions of years, but billions of empty light years, whispering the story of how the cosmic web was woven. Each discovery brings us closer to understanding the balance between matter and emptiness. If our part of the universe is indeed less dense, these instruments will measure that directly. They will track how galaxies drift through the hollow, how dark energy accelerates their separation, and how light from the far side of the void arrives slightly dimmer and redder. These are delicate clues, but in their patterns lies the truth of our cosmic home. There is poetry in this search. When ancient people looked up, they saw stars and gods. When Galileo looked up, he saw worlds. Now, when we look up, we see the fabric of space itself, woven from gravity, dark energy, and time. We are not just stargazers anymore, we are mapmakers of infinity. But even with our best tools, there will always be mystery. The universe is too vast, too old, too strange to ever fit neatly into a single equation. Some scientists dream that one day we might see the entire structure from above, every void, every filament, every glowing thread. Yet perhaps that will never happen. We live inside the map we're trying to draw. We can only explore it one light beam at a time, and maybe that is enough. Because each observation, each experiment, each act of looking outward also teaches us something inward. That curiosity itself is part of the universe's story. The cosmos is aware of itself through us. When we gaze through these windows to the infinite, the universe is, in a way, looking back. The farther we look into the universe, the more we realize that silence is not empty. It is full of meaning. The great cosmic void that surrounds us, the vast KBC Void, is not a place of nothing, but a space of quiet balance. It is the pause between creation's words, the stillness that allows light to travel, galaxies to grow, and time to unfold. And within this silent space, life itself has found a home. When we imagine the word void, we think of loneliness or absence. But the truth is more gentle. The void is not a hole where something is missing. It is the background against which everything exists. Without emptiness, nothing could move. Without space, light would have nowhere to shine. The universe needs its hollows just as music needs silence between notes. Inside those pauses, harmony is born. Our Milky Way drifts through this calm region, surrounded by the invisible threads of the cosmic web. To the human eye, everything looks still. Yet every second, space expands a little more, carrying galaxies farther apart. The distance between clusters grows by millions of kilometers each minute. It happens quietly, too slowly to notice, but it is always there, the breath of the universe steady and eternal. If you could step outside the galaxy and look back, you would see our spiral shining faintly at the edge of a great cosmic valley. Beyond it lie other clusters, other filaments, like glowing mountain ranges in a night without end. The light from those distant peaks takes billions of years to reach us, crossing the thinned air of the void. By the time it arrives, it has stretched, cooled, and softened into the background hum of creation. That hum surrounds us always, like a memory too old to fade. In this silence, we find the heart of existence, a place where expansion and gravity balance, where the universe becomes still enough to think. It is strange to imagine that inside a region with so few galaxies, consciousness could arise on a small, fragile planet orbiting an ordinary star. But maybe that is the universe's secret. Awareness blooms not in chaos but in calm. Just as seeds grow best in soft soil, perhaps thought itself grows best in stillness. The void around us is not dead space. It is the stage on which the universe performs. It allows time to move, light to travel, and matter to gather. The galaxies that surround our hollow form the walls of this invisible chamber, and we, unknowingly, live inside it, measuring its size, tracing its edges, and wondering why we're here. Some scientists believe that, in the far future, the void will grow even larger. As dark energy continues to push the universe apart, galaxies will drift beyond the horizon of visibility. Their light will fade into red shadows, and only our local group, the Milky Way and its neighbours, will remain visible. The rest of the cosmos will dissolve into silence. For the beings alive then, the universe will seem small and still. They will not know how vast it once was. But for now, we live in a moment of great clarity. We can still see billions of galaxies, still measure the afterglow of the Big Bang, still feel the faint pull of distant matter. We are lucky travellers in time, born between the beginning and the dimming, when the cosmos still speaks loudly enough to be heard. When we look at the night sky, we are looking through billions of years of history. Every point of light is an ancient message that survived the journey through emptiness. Each one reminds us that even in the quietest corners of the universe, something is always happening. Hydrogen turns into stars. Stars create heavier elements. Those elements form planets, oceans, and life. Even silence creates. The idea that we live in a void can make some people feel small or isolated, but it can also bring peace. The emptiness around us is not a prison. It's a cradle. It gives our galaxy room to breathe and space to evolve. It shields us from the chaos of crowded clusters and allows our sky to shine clear. Within that openness, life on Earth had time to grow, to learn, and to dream. The void, then, is not the absence of meaning, but its possibility. It is the space in which meaning can unfold. Just as an artist needs a blank canvas to paint upon, the universe needs emptiness to express its beauty. Think of it. We exist in a balance so perfect that matter and nothingness share the same stage. The galaxies are the bright strokes of colour, but the void is the quiet background that gives those colours depth. Without it, the universe would be flat, lifeless, and still. In the grandest sense, we are not separate from this emptiness. We are made by it. Every atom in our bodies was once part of a star that drifted through the cosmic web, born in density but expanded by the same void that surrounds us now. The space between those atoms, the tiny gaps inside every molecule, is the same emptiness that fills the universe. The void is not out there, it is within us. And so, as we reach the end of this journey, we return to the beginning, to silence, to stillness, to awe. The universe is vast beyond imagination, yet in its quiet heart, it carries a reflection of our own search for meaning. We are creatures who arose inside a hollow of space and light, yet we fill that hollow with thought. memory, and love. Perhaps that is the final secret the Void teaches, that even in a universe ruled by silence, something beautiful can speak. That in the cold and endless dark, warmth can appear. That in the quiet heart of existence, life can listen and light can dream. So as you close your eyes tonight, imagine yourself floating gently through that cosmic stillness. Feel the faint pull of gravity, the breath of expansion, the rhythm of galaxies drifting like lanterns across the dark sea. Let the silence hold you. The universe is vast, but it is also kind. Rest now, child of the stars. You are part of the Great Hollow, and the Great Hollow is part of you. The universe expands, and so do you, with every heartbeat, every breath, every dream.